All right, good morning. Let's get started. We'll continue on the concept of system causality. So a little bit heads up, I think from here, maybe the next couple lectures, or maybe in the whole term of lectures, things are going to be a little bit abstract. This is a very typical response that I have received in the past for this part of the course material. Okay, so just a heads up, but I'll try my best to make it as clear as possible. So at the end of the previous lecture, we talked about a concept called signal causality. So if you look at your lecture notes, you'll see the definition of that. Signal causality is different from system causality. Okay? So signal causality is fairly straightforward. As long as the signal is not zero, when t is less than zero, then you have a non-causal signal. Right? So now let's take a look at what system causality is. So first, let's present the definition first. A causal system is a system for which the output at any instant t naught so we're talking about output here. Okay. And this output at any instant t naught depends only on the values of the inputs so let's call this input is f of t. Okay. I'll draw a graph here for t that is less and equal to t naught. Okay, so this is a more very shortened version of the definition, but so let's take a look at how we interpret it. Okay. As you recall, we can always represent a system using a box, and we can give the system with certain input. So let's call this as f of t as the input at here. And then the system will produce an output. So let's call it y of t. Okay. So inside the system, it has some magical operations going on. Right? Whatever spits out of the system, right, the y of t, it could be exactly, right? For example, y of t could be exactly the same as input. Right? That's what the system does, basically. Or the y of t could become a negative of this. Or y of t could become a shifted version of the input. Right? So those are very simple example of what output could look like, right, given certain system. Right? Okay, so now I want to clarify a few things. Okay, I have noticed some common mistakes in the past. So this is kind of review it here, right? So we did a review. You know, we know this is called a function. Right? This is a function. Okay, mathematically, I mean, of course, here it represents an input, but this is literally just a function. Right? So what does f of a t naught mean? Right? F of t naught. So f of t naught is you replace the t with t naught. The function could be anything, right? Could be t squared or sine t, right? So sine 2t. So function can be anything, or signal can be anything. So when you're saying, when we're referring to the function at the t naught, this is so basically you get the t naught square, or sine t naught, or sine 2t naught. Right? So depending on the expression of the function, so you will end up with corresponding expression. This is the value, right? You plug in a certain time instant t naught into the function, you get a value. Now, common mistake is, okay, I didn't have a specific values here. Sometime maybe I have a f of 2, or maybe sometime we just have f of t naught. Okay. A common mistake for you is to realize this doesn't mean this is f times bracket t naught, because I've seen that so many times. Right? So people sometimes interpret this as f times 2, for example. Right? And this is completely wrong. This here means this is the value of the function at t equal to 2. Right? So over here, this basically means this is the value of f at t equal to t naught. Well, let's be crystal clear with this. Okay? That kind of mistake should not happen. Okay. Good. So now the question here is back to the definition of the causal signal system. A causal system is a system for which the output, in our case, this is output here, okay, at any instant t naught depends, and this is very critical, depends only, right, on the values of the input for t less or equal to t naught. So let me give you an example here. Okay? Very simple example. So let's say f of t, y of t, okay, is basically the same as input f of t. Good. Right. So now, according to the definition, I'm going to bring in a instant, okay, any instant t naught. So if I replace the t with the t naught, then the expression at here means this is the output of the output. This is the output value at t equal to t naught. That makes sense, right? So that's the output. So according to the system, what is the output then? The output is f of t, so this is equal to f of t naught. So then you look at this expression here. If I had to describe it using simple words, this basically means the output at t equal to t naught depends on what? Depends on the value of input at, according to the expression here, t equal to t naught. So that's what this expression tells us. And it actually only depends on the value at the t equal to t naught. You look at the expression, right? So does it depend on the value at the t naught minus 1? No, it doesn't, right? Yeah. So of course, I'll give you another example. You'll see maybe, right, it depends on some other values of the input. But this one here, the output only depends on the input value at the t equal to t naught. That's how you interpret this expression, all right? Yeah. So then let's see if I give you a slightly different example. Okay, so let's call this example 1 and example 2. Oh, actually, before I move on to example 2. So look at the example number 1. Now you go back to the definition. What would be your conclusion for the current system? Do you think it's a causal system or non-causal system? It's causal, right? Excellent. Because that's what it says, right? Depends on the value only for, of course, we're not depending on any value less than t naught, but that fall into this range at here. Okay, very good. So let's take a look. So this one, basically, I will see the system is causal. So let's take a look at the second system. Y of t, I'm using red color, let's go back to the blue color. Equal to f of t plus f of t plus 2. Okay. So let's try this one. So f of t plus f of t plus 2. This is a new system. The output equal to the original input, and then plus a shifted version of the input, plus 2. If you go to this week tutorial, you will see the reviews, right? Plus 2 is shift to the which side? The left or right? The left, right? Good. So now the question, of course, is we want to check if the system is causal or non-causal. Okay. How do we check this? Okay. So we have to check this precisely based on the definition of the system causality. Okay. So according to the definition, right, you introduce a time instant. Now, if you're not comfortable with a symbol t naught, you can certainly use an actual value at it here, right? So you could see, okay, at the t equal to 2, for example. Okay, that's perfectly okay. So if I introduce a time instant, then according to the output, y of, I'll use t equal to 2 at here. Okay, just I know a lot of times students, they stay a lot of time not comfortable with pure symbols, right? So what is the value of our system output at t equal to 2? So here's my system, right? So according to the system, you have f of 2 plus f of 2 plus 2. So you see what I'm doing? I'm replacing all the t with the value of 2 here. Now you might actually wonder, and this is a very common question for now. So you say, what is f of t? Right? Now I didn't give you f of t. As I mentioned, f of t could be anything. Right? It could be any time functions. Yeah. So you don't have to worry too much. But the thing is, we're always comfortable with everything specified, right? Yeah. Okay. So now I have the expression here, which is f of 2 plus f of 4. So my output equal to f of 2 plus f of 4. So this is where for you to start to interpret this expression here. Interpret is exactly what I just did over here, right? So using Word, I see the system output. I mean, I don't have to write this every time, okay? But of course, for starting point, you might want to write to clarify, to clear your head. So the system output at t equal to 2 depends on what? You look on the right side. Depends on the value. So this time, and not just one value, all right? You have 2 values here. So it depends on the values of input. First one, the value of the input at t equal to 2. And the second one, the value of the input at t equal to 4. Right. So this one is input value. This is the input value at t equal to 4. So the next step, you draw a conclusion now, right? Draw a conclusion. See, is our current output relevant or depending on any one of the future inputs? See what I'm saying, right? So you see here, now this is basically bringing the idea of a future or past. So when we say t less than t naught or less equal to t naught, right, for f of t, for the input. So the less sign basically means is past input. The equal sign means what? The current input, okay? So over here, the current example right here, basically the output depends on the current input And this one here, what do we call that? Future inputs. Right? So you could write one more words here. You can see, so y of 2, right, depends on current and future inputs. So finally, you can draw a conclusion. Anything depends on the future inputs. Any system that depends on the future inputs is a non-causal system. Okay? So you can see the system is non-causal. All good? Right. And this actually backs for a philosophical question, right? So if you are into philosophy, very common one is cause and effect. So no cause, no effect, or no cause, there is the effect, right? So no cause and there is effect. There's, anyway, so we're not getting too much details here. So non-causal system, basically no cause, no effect. Okay. So I think if you take a moment to sort of think about what we just have described the causal system, how you can determine a causal system. Right? So what do you need to basically be clear with? Number one, right? What is the input? Right? What is the output? What is the relationship between the input and output? Okay? And how does the output, right, value depends on the input value? What's the meaning of current? What's the meaning of a current input value? What's the meaning of a past input value? And what is the meaning of a future input value? Okay. So all of this simple concept, if clear, and then you relate back to the definition of the system causality, and you can make a decision whether the system is causal or non-causal. Good? Yeah. So your a few comments that are here. Okay. First of all real-time physical system, okay, are causal. All real-time physical system causal. And you will only see non-causal system in science fictions. So unfortunately, we cannot predict. We can predict, but we can never really predict the future, right? So mathematically, you can certainly construct non-causal system, but unfortunately, real-time system are all causal system. Okay? Or in other words, time only moves forward, right? So you cannot grab a actual future output, right? Actual future inputs. Okay? You can never know what the future input is. Sorry. However, there's a little bit of there's a little bit differences for some digital system, okay, for system processing, for signal processing. It does not apply. So what it means is that computer, if I talk, then the computer digitizes the voice and then distort it, right, in the computer as a file, right? So and then computer, maybe you use some other tools to process this sound. Right? So basically, what you're doing here is you're processing digitized signal which already have passed. And you can still construct a model, though, right? You can still construct a model based on this set of data. And this model will sometimes probably appear to be the current output actually depends on the future input. But that's not exactly what we're saying in here, right? Because you're processing already happened information. Okay? So that's why for signal processing, this causality should not apply. Another causality that should not apply, I should just skip it here, is that spatially varying signal does not apply. So if you go to do an MRI, they do a scanning of your body layer by layer, right? So there is really no, past or current information. It's just a spatial information, right? So that also does not apply here for causality. Okay, so to be in a very simple language, right? To be in a very simple language, if you want to reiterate this one here, maybe I'll just write it on one more line right here. Okay, I should say in a causal system, the output cannot start before the input is applied. Before the input is applied. Delay is fine. And that's more less math expression, more of just a simple expression. Right? Delay is fine means, you give a signal to the system. So you give a signal to system at exactly t equal to 2 seconds, for example, right? And you observe the system output. You waited, boom, the system produced an output at t equal to 4 seconds. And that is okay, right? So it basically means there's a delay in the system. And that actually is very common in the physical world. Okay. So let's take a look at a few more examples here, okay? And I know this part, especially at the beginning, it's hard to sometimes materialize to visualize this thing here. You just have to have a fully understanding of the concept and then apply it, okay? And then you see the decision. Okay? So let's take a look at this one here. Okay, so this first another example. So let's call it example 3. So here's another system. Yeah. Of course, when you're presented with the certain system, the first step is to be clear, or maybe the system, the question's already telling you specifically, right? X of t is input, y of t is output. So that's what you really have to be very clear. What is the input? What is the output? Right? And then you try to determine relationship. Good. So let's look at this one. Now here is, if you want, you can also produce a box, a sort of like a box diagram like this one here, right? Just to help you out with the structure. Okay. So without me actually going into it, let's all think it together here, right? If I want to see the causality of the system, okay, let's try to review the concept. I can introduce a time moment. Okay, any number is fine. And then I'll look at the input-output relationship. Particularly, I'll see the output value depends on what kind of input value, right, for this question. So that's the procedure, right? Okay. So I'll see, I'm not going to see anything. I'll just see, okay, so y over 2, let's for example. Okay? Yeah. I'll write it down here now. Yeah. So now you go back to your observation. The current output value depends on where is the input in the expression. Here. So you do not confuse yourself. Okay? This term, this is not an input term. Right? This is just some sort of a term due to the characteristics of the system. Okay? So basically, I want you to be crystal clear when you have an expression. Which term is the input? So don't be confused by any other additional terms that are not actually input terms. Okay? So this term here, and whatever you want to call it, okay? So this is just a term, okay? It's a term due to the system. Good? Yeah. And if I have to maybe draw this out, maybe what happens is, let's say this is a system, and this is your input x of t. Then inside the system, right, you have, so this x of t goes in here, right? And then I would see maybe there's another box over here, produce cosine t, right? So this box multiplied by the input value x of t, and then you have, let's say, juncture here, maybe just a constant 1, right? And that produce the output y of t. Right, so this is probably what's going on inside the box, which is representing the system. Okay. All right, good. So that's pretty much all the information you need, right? Then you go back to your definition of causality. Now you answer me the question. Do you think this is a causal system or non-causal system? Non-causal. Huh? Is it a causal system or non-causal system? Pardon me? Non-causal? Can you explain why it is non-causal? Yes.
Yeah, so basically they're like not like completely dependent on the input value, so there's plus one, and there's a cause which is actually affecting the output result.
Okay, so again, you are saying the output is not completely dependent on the input value. Yes. Okay, so this is where exactly I'm trying to clarify the confusion at it here, right? When you look at the causality, what do you look at? Set aside everything else. You only look at what? The input and the output. You do not look at anything else. What is input? Here. What is output? This. Do not look at this term. So now can you see, is it a causal or non-causal? If you only look at the relationship between the inputs and outputs. Yes, it's causal, right? So if you have to see it in a simple language like what I've written here, the output value, okay, the output value depends on what kind of input value. What do we call this? The past, the current, or the future? Current, right? So in this case, the output value depends only on the current input value, which is fine, which is a part of the allowed concept in the causal definition. Yes?
Just a question here.
Yeah.
So, to determine if a system is causal or non-causal, we just see if there are multiple single inputs, right?
We're focusing on single input, single output now, yes.
But if there's multiple inputs, like different value, like f equals to 2 and f equals to 4 is non-causal.
If you're referring multiple input, multiple outputs, you actually have exactly the same kind of definition, right? So basically, you have the output depends on any future inputs. Doesn't matter which one of the inputs, right? So the idea is still the same. Does that make sense? Or do I understand your question correctly? Yeah. Okay. Is that clear? Okay. So over here, you could clearly see, as I said, right, the relationship, right, so y of t, I can see y of t depends on only the current input value. So that's why this is a causal system. Now you might wonder, how would you know that y of t depends on only the current? Because you have only picked one time moment 2, right? You only picked one time moment 2. And that is a very legitimate question. The question here is, when you check causality of the system, you really have to check the whole range of the t, right? From negative infinite to positive infinite. Okay? You have to check everywhere. But of course, you can't check everyone, but right? But there is the other reverse. If you can find one that gives you actually a different idea from what I have written here, or that's different from the definition, right? Then you can prove that the system is non-causal. Okay, I'll give you an example shortly, right? But this one is fairly clear. Is you give an example you see here, and then you also can observe from the current system description. The output at the t depends on the input at the t, which is the current, right? So that's another way to basically to examine this. Yeah. A little bit varied version of this question. Okay, so let's see if I change the question to 1 plus x of t times cosine t plus 1. Okay, so let me change this to x of t times cosine t plus 1. Okay, so this is the difference set here. Okay. Now let me ask the same question. Okay, let me say, anybody tell me, is this a causal system, or is it still a causal system, or is it become a non-causal system? It's a causal, right? So do not be tricked by this additional term here, because this is not input, right? The relationship between input and output is still holds, right, as we said. Yes?
How do you know that x of t is the input there?
Because the question will tell you, right? So x of t is input, y of t is output. Yeah. Right, like this. Yeah. And that's a good question, because you know when you have presented the question, this is exactly what I mentioned, right? Identify which one is the input, which one is the output. Okay. If the question didn't clearly say that, then you should raise the question to the instructor or to me, right, to ask what is the input, what is the output. Okay, let's take a look at one more this example here. This one is a little bit challenging than the other one. Okay. So let's take a look at this system and see if this system is a causal system or a non-causal system. So this integral from 0 to infinite, integrating x over t minus tau, and then d tau. Okay? Yeah. Okay, so technically, I'm going to try to follow exactly my way of thinking, right, for determining system causality. You could just say, okay, I'll introduce a time moment. And at this time moment, and you get this. Good. So let me see if anybody actually actively thinking can make a conclusion based on this one, based on this expression here, or this expression, doesn't matter, right? By relating to the definition. Yes, go ahead.
This is like a little bit guesswork, but this expression for infinity is 0. Isn't one of the parts connected equaling 0, one of the parts equaling infinity? So it's causal?
It's causal? Yeah, the conclusion is right. It is causal. Okay? So the 0 to infinity, first of all, the integral limit is 0 to infinity. Let me ask you this. It applies to which variable? Which variable's range goes from 0 to infinity in this expression? Tau. Right? Very good. So the tau's range goes from 0 to infinity. Now, if I have to explain this a little bit in a more intuitive way here, I want you to go back to your 172, maybe the first initial lectures for 173 actually, when you learn integrals. When you learn integrals, what's the starting point? Integral is what? It's approximated addition of some rectangular boxes underneath a curve. You remember that, right? You know, of course, we all know the conclusion. When you integrate a certain curve, the integral gives us the area underneath the curve, right? Yeah. But the way how it's derived is you use the limit concept. You know, basically, For example, right? So let me maybe just quickly go over this. Suppose I have a function x of t, and you integrate it from 0 to, let's say, to a, right? dt. Or you can just use a tau here, that's fine. Okay. So how does this integral is calculated or is approximated? So what you do is you create many small rectangular intervals, right? So each one of these, you can call them as a delta t. And then you can create basically rectangular boxes, right? There's two different ways to create the rectangular boxes. And then you can see now, okay, so the area underneath the curve x of t, so the area underneath the curve x of t is approximately what? Is approximately the height at here times the bottom length. The height at here, let's say call it x of 0 times delta t, right? And the next one here is, let's say, x of 1 times delta t. Okay. And then you add up to x of maybe n times delta t. Okay. So you have an n number of rectangular boxes, you add the area up, and then you get approximately the total area underneath the curve. And then as basically this n go to infinite, if you separate this bottom interval into infinite number of intervals, okay? So the top expression in here can be written using the summation sign. Right? Summation sign basically means your, for example, n equal to 0 up to number n here, then you x of n times delta t, right? That's summation sign. So as n go to infinite, this summation sign becomes integral sign. Right? So the summation sign is approximation. Integral is the accurate value. Right? So as n go to infinite, the summation becomes infinite. It becomes integral. And then you have a limit, 0, let's say, to a. X becomes, let's say, call it tau here. Delta t becomes d. So the delta becomes straight d. Right? That's the limit concept. Small change becomes differential change. Right? So you basically get the integrals here. That make sense? So basically, behind the integral, right? So now I want to basically establish a simple concept. Behind the integral, what's actually going on here is you have a value of x within the range of these integral limits and multiplied by a very small quantity, a delta t, a change, right? And that delta t is also part of the interval within this 0 to a, okay, or integral limits. All good? Okay? So now if I go back to this question here, right? You think about if I really wanted to use the actual the approximation concept as I illustrated here. So how would I approximate this integral? Right? How would I approximate integral here? Because tau goes from 0 to infinite here, right? So I guess what I could do is, here's a t naught. So the tau here may be like what I did. I start from 0, right? Because the limit goes from 0. So minus 0. And then multiplied by a certain interval, very small interval at the bottom there. Okay? And the next one is x of t naught minus, let's say, call it 1. Okay? And then multiplied by another small interval, delta t. Okay? So delta t here, you got to keep in your mind, delta t here is it's a quantity. Right? It's a very small quantity. How small, depending on how you are sectioning the bottom, right? 0 to infinite. So now you can imagine what happens is until you reach what? X of t naught probably minus, because it's infinite, so I guess, I could probably just minus infinite, right? Yeah. And then might multiply another delta t at the end. Okay? So the original integral basically becomes this algebraic expression. Good? So I think now you actually be able to answer the question. So you look at this current expression. Okay? So can anybody tell me, is this a non-causal or a causal system? Maybe before you see the conclusion, I want you to think in your head to describe it. The current output, okay? The current output, does it depend on the future input, or does it depend on the current input, or does it depend on past input, or does it depend on a combination of some of this? Okay? Yes? Depends on the past input. Does it depend on current input? At some point? Which point? Yes, right? So more precisely, what you just, if I summarize, the current output depends on the current input and past inputs. Do you see ever in this expression any future input comes up? No, right? So basically your conclusion, without writing what I just said here, so the conclusion is the system is causal. Good? So this is a little bit complicated question, but as you can see, when you break it down, you are essentially still applying exactly the same approach, right? Which is the definition of the system causality. Very good. So I want you to give you a different example just for you to kind of critically think yourself. Okay. Okay. So let's suppose that actually this is not sorry. Let's see. Sorry, should be 0 to t. Let's use 0 to t here. Sorry, I was just using this when t. I plug in the number. Okay, if you have a different integral system, you have a different integral system here. Right? What is the causal or non-causal property for the system? Okay. So the difference here is you have a variable t at here, a little bit different from this one here, right? The integral limit here, this is literally it's a number, right? Infinite. Okay. Your t resides inside the integral. But here, your output t comes from this integral limit t. Okay. Yeah. Okay. So when you have this kind of situation, right, you could certainly, what you could do is you could certainly try exactly the same approach. So let's say let t equal to 3, and then y of 3 equal to 0 to 3 x of tau d tau. You don't like 3, you can 4, 5, 6, 7. Okay, it doesn't matter. Okay. But once you try a few numbers, and you actually will get a pretty good sense. So, but just looking at the t equal to 3 moment, do you think the current output depends on any one of the future inputs? Right? Do you think that? No, it doesn't, right? Because if I use exactly the same concept that I illustrated here, 0 to 3, for any of those input, it's all current and past input, right? So this is checked out. This is basically means causality, right? Causality. However, right, as I said, you have to be careful. When you check causality, what do? You check all the range of the t, okay? All the range of the t. So you're not just checking positive value t. You have to check all of this. So this is, let's say, what about if I let t equal to -3? Okay, so let's see what happens, right? So if I have a -3 here, so y -3 equal to 0 to -3 x tau d tau. Then this is equivalent to -3 to 0 x of tau d tau. Okay? Yeah. So what's current output? Current output is y of -3 at the t equal to -3, right? What's current relationship between current output and input is this. So then you see does the current output depend on any one of the future inputs or not? Okay, based on the current expression. I see a lot of nodding. That means you observe the current output actually depends on the future inputs, right? Yeah. Very good. Because why? Because if I get back to the original approximation concept, the integral limit goes from -3 to 0. So what's involved here for the inputs? It involves x -3. It involves probably x -2. It probably involves x -1 or an x 0, right? So what's involved here has infinite. Of course, I'm going to illustrate a few. But you can already tell your current output at t equal to -3 depends on this. -1 comparing to -3 time moment is the future. Right? So that's why for the current example I have already picked it here. And I demonstrated that at a certain point, the system actually depends on the future inputs. So as long as you can find one example, you don't have to find all examples. As long as you can present one example, then you can conclude that the system is actually non-causal. Okay? Yeah. So you can see system is non-causal. Good. Of course, right, you have to be very careful. Math is always a precise business. Now, if the question says, given the current expression, and then the question says t is greater and equal to 0. So it specifies the t's range. Okay? If the question has this there, then your conclusion is causal now. Okay. So just watch out some of the little details. Right? Yeah. So I should probably write another words here. So when t is greater than 0 or greater or equal to 0, right, the system is causal. Good. So I don't have much time, so I don't want to introduce a new concept. Maybe let's just have one more simple example here, okay? So let's continue to stimulate our brain until we know exactly what we need to do in terms of determining the causality of a system. Okay. So yes. Oh yeah, go ahead. What is it? Oh, you don't want to answer this one. Okay, go ahead. Sure. Yeah. Good. Yeah. Sorry, what's your name again?
Or you can call me Bert.
Bert?
Yep.
Yeah. That's really quick thinking, right? So when you started, this is already answered because you observe already, right? When t is less than 0, and you have an input depending on the future inputs. Okay. So very good. You know, he stole my thunder. But that's exactly what I want you to do. Okay. So what you do is, I want you to check t greater than 0. Check t greater than 0. What is the causality? And check if t is less than 0, and what is the situation. So essentially, when you're doing the checking at it here, right, when you do the checking, chances are you plug in a t value. Okay? So it doesn't matter what value you plug. When you plug in a negative value, right, and you will actually see that relationship right away. Okay. Good. So try it out, right? So let's say y negative 2, right, equal to x of 2. Okay. That's pretty obvious, right? Yeah. Good. I will stop here, and the first week assignments should be given out this week, I believe. Okay. So you have some exercise to do. Right? Yeah. Any questions? Feel free to come over.